Hey everybody, today we're talking about section 12B, sorry, here we go. 12B, dilations of functions. When something gets dilated like your pupil, it can get bigger and smaller, but stays in the same shape. So a dilation is what we call a non-rigid, meaning it doesn't stay the same shape, or excuse me, it doesn't stay the same size, but it does stay the same shape. It's a non-rigid, which means it enlarges or compresses. And this can be vertically or horizontally. Okay, so let's talk about what that is going to look like. So as we're looking here, I notice that this 2 is outside the function or outside the parentheses. I know that that means it's a vertical change. This 2 also means it's being multiplied. So this is a vertical stretch by a factor of 2. So that means vertically, and aka its y value or its vertical height is going, everything is going to double by 2. So this will double the y value, okay? So if we see here at this point, this y value is at 3, which means it's going to double to 6. The x value doesn't change. The y value does. Here, we've got a y value at 0. 0 times 2 is still 0. Here, we have a y value of 2, so it's going to double to 4. And back here, we're at 0, so it's not going to double. And we're just going to connect. You could do more points than this, but you just really have to do the most critical points so you can get the shape of the graph. All right, let's look at this one. This one, we see a 1/2 in front of the function outside of the parentheses, so I know it's vertical because it's outside of the parentheses. And it's being multiplied, so I know this is going to be multiplying by a factor of 1/2. When I multiply something by a 1/2, or I take its height and I cut it in half, this is a compression. So if I'm going to compress every y value by 1/2, so like for this one, this value was at 3. Well, half of 3 is now 1/2. So this is going to go right here. 0 times 1/2 is still 0. At 2, right here, it's going to cut down by half, so that's going to move to at 1. And then at 0 again, 0 times 1/2 is just 1/2. So these new values are here. And we're going to emulate that same shape. All right, so now let's talk about how do we deal with horizontal dilations. Remember that horizontal changes happen inside the parentheses. So I see a 2 inside the parentheses. This tells me that it's going to be a horizontal. But remember, inside the parentheses, everything is funky, which means everything is opposite from what it seems. Before, when we were doing shifting, adding a number really moved it to the left. Subtracting a number really moved it to the right. Now that we're multiplying, the opposite of multiplication is division. So this 2, multiplying by 2, is actually dividing by 2, which is a compression by a factor of 1/2. So that horizontal stretch, or that horizontal distance that we have right now, everything's going to become horizontally shorter by 1/2. So for example, at this point right here, the horizontal distance is -4. Half of that is now going to be -2. The y value is not changing. Here, at this point, the horizontal value is -2, so that new value will be -1. On this point, it stays the same because a horizontal distance of 0 is still 0. And here we've got a horizontal distance of 2, so now it's 1. So I'm going to change everything. So do you see it's kind of like I took 2 hands and I squished in the original red graph to become the pink graph. All right, let's look at this one. Again, this change is in the parentheses, which tells me it's horizontal. Remember, it's funky town, so it's not really multiplying by 1/2. It's going to multiply by a reciprocal, or the opposite of it, which means it's going to stretch by a factor of 2. So everything horizontally is now being stretched outwards by double. So this, remember, was at -4, and now it's going to be at -8. This point is at -2, so now it's going to be at -4. This point is at a horizontal distance of 0, so it's going to stay there. And here's 2, so now it's going to be at 4. And so we're going to connect these most important points to give that shape. So it's the same shape as the red graph, but everything's been doubled in size horizontally. All right, now let's look at this one. We see that there's a negative inside the parentheses, which tells me it's a horizontal. Remember, multiplying by a negative means it's going to be a flip. Now I want you to think if something is flipping horizontally, use your hand in the air. If something's moving horizontally, it's going to flip over the y axis. Okay, so that means here that if this is 3 away from the y-axis, it's now going to go 3 the opposite direction. It's going to be right here, okay? If this point here is -1 to the left, it's now going to go 1 to the right, and so on. So I'm going to recreate this graph. This is going to stay right where it was. This point is going to be now here, okay? So then we see this is, do you see how this is the V, but it flipped over? And then this was at 2, so now it's going to be at -2, so these 2 points connect like that. So we can see that the red graph is now flipped over the y-axis to the green graph. All right, let's look at this next one. So given the example, we've got a couple of different transformations here. I see this one here is outside the function, so it's going to be a vertical. This is multiplying, so it's a stretch by 3. Remember, it's outside the parentheses, so we can trust it. We're not going to change that number. So we're going to vertically change everything by 3. So this vertical distance is 0. It's going to stay there. This vertical distance is -2. It's now going to multiply by 3, so that would be -6. This vertical distance is 0. It's going to stay there. This vertical distance is 1, so it's going to multiply by 3. And this is also 0. So this is my vertical stretch, okay? Now, I'm going to also look here. This is a addition outside of the parentheses, so it's a vertical shift up by 2. So every point is now also going to go up 2. So we move this up 2. Every point that was already stretched is now just shifting up by 2. And now we can connect those dots to make the final drawing. All right, let's look at this one. So we have a few things going on here. We see a negative, we see a 2, we see a 3, and we see a 1, okay? When we're dealing with both vertical, right? So we see some vertical, here's a vertical flip. This is a vertical shift up 1. And then we see some horizontal transformations inside the parentheses. So this is a 2. That would be a stretch if it was outside the parentheses. But because this is Funky Town, everything is opposite of what it seems. So this is a horizontal compression by 2. And this is a horizontal shift to the left because the opposite of plus is a minus. So when we've got all of these different things going on here, both horizontal and vertical moves, our moves are first going to move horizontally because those are inside the parentheses, and PEMDAS says we do inside the parentheses first. And we're going to deal with stretches and compressions first, and then any shifts. Okay, and then the second moves we're going to deal with are the vertical stretches, and then the shift. Okay, so let's deal with the horizontal moves first. And I'm going to color code this so you can see. The first thing we're going to deal with is this 2. This is a horizontal compression because it's Funky Town by 1/2. So I'm going to take every horizontal distance from 0 and cut it in half. So this was at -3. Now it's going to be -1.5. This was here at -1, so now it's going to be at -1/2. This was +1, now it's going to be +1/2. This distance horizontally was 2, so now it's going to be 1. And this here was 0, so now it's, 3, now it's going to be at 1.5. So this looks like this. Okay, so that's our horizontal compression by 1/2. Now I'm going to deal with this horizontal shift to the left 3, because remember, everything's funky, so a +3 is actually going to the left by 3. So all of those points are going to go over 1, 2, 3, 1, 2, 3, 1, 2, 3. Here we go. 1, 2, 3. And 1, 2, 3. Okay. Hopefully you're color coding this so you can really see what's going on here. Okay, so that's that hot pink change. Let me just kind of, whoopsie, go back. I'm gonna clean this up a little bit just so we can see what's going on, where the pink is and all that stuff. So our new changes are gonna be based off everything we just did with the pink. Okay, so I'm just gonna give myself a little bit of something so I can see what's going on. Okay, so this is the result of all those horizontal changes. Okay, so now we're on to those vertical stretches and then a shift. So this counts because it's being multiplied. This is a vertical reflection. Remember, if something reflects vertically, it's going to change this way. So it's going to be over the x-axis. So I'm going to take every value on my new pink point and I'm going to flip it over the x-axis. So this one right here is on the x-axis, it's gonna stay. This one here is at -2, so I'm gonna flip it up to +2. This one's on 0, so it's gonna stay. Here's also on 0, so it's gonna stay. This one's gonna flip down. So now, here's my new graph. It's just been flipped upside down over the x-axis. And now the last thing we're gonna do is we're going to do this vertical shift up 1. So I'm going to take every point and shift it up by 1. So this is our green final graph. Okay, let's look at some algebra. So this will be a little bit easier as far as numerically goes. So if we're given f of x is x squared minus 3x, then let g of x equals twice that function plus the 4. So remember, these are both going to be vertical moves. This is going to move it vertically. It's going to be a stretch by 2. So remember, everything's going to double. And then we're going to add 4, which is going to shift it up vertically by 4. But we can do this numerically by saying, well, g of x is twice of, well, what's f of x? F of x is x squared minus 3x plus 2. And then we're going to add 4 to it as well because that's our double f of x plus 4. Now we're going to distribute. So we get 2x squared minus 6x plus 4. Bring down this plus 4. And if we simplify, we get 2x squared minus 6x plus 8. And that is what the result would be for that transformation of that function numerically or algebraically. Let's look at this one. So we've got f of x here. 6x plus 3. So if I'm going to look at this, remember this is going to be a vertical compression by a factor of 1/3. So everything's getting vertically shorter by 1/3. And this is a horizontal shift where everything's going to go to the left too. But if I want to do this algebraically, I'm going to say g of x equals 1/3 of f of x. Well, f of x is just 6x plus 3, okay? But remember, this part here says, hey, we want x to actually be x plus 2. So instead of x, I'm going to replace it with this x plus 2. So now I'm going to evaluate this. So I'm going to do inside parentheses first. We're going to distribute. We get 6x plus 12. And then add the 3. So this becomes 6x plus 15. Multiply everything by 1/3. And we get 2x plus 1/3 of 5. 15 is just 5. So g of x equals the result of 2x plus 5. All right, let's look at this numerically. So numerically, it says let g of x equals 5 times the function of x minus 1. Find g of -1. So remember, if I'm going to look for g of -1, every time I see x, I'm going to input it with -1. So we're going to go 5 times f of x, where x is -1. minus 1. Well, what is f of negative 1? So I input negative 1, we get out 12 out of the f of x function. So I'm going to replace this with 12. So what's 5 times 12 minus 1? It's 60 minus 1, which is 59. All right, let's look at this one. It says, given the table of values, let g of x equals f of 3 times x minus 1 plus 2. Find g of 2. So again, we're going to plug in every time we see x, we're going to use 2. So instead of f times 3 of x, it's going to be 2 minus 1. Then we're going to add 2 to that. So here we go. Inside functions first. So we go 2 minus 1 is just 1. So we're looking for f of 3 times 1. Well, we know 3 times 1 is just 3. So now we're looking for just, hey, what's f of 3? Well, when I input 3, I get out 8 out of my function. So I know f of 3 is 8. Add the 2, we get 10. All right, last one. Let's talk about the domain and range. So the domain goes from -2 to 5 inclusive, and the range goes from 4 to 9 non-inclusive. If g of x equals 3 times f of x plus 2, this means a couple different things. Remember, this 3 means that it's going to be a vertical stretch by a factor of 3. That means everything, if we're dealing with vertical, that means everything y values. So this means that y values multiply by 3. So let's do this first. So if we were going to do a vertical stretch by a factor of 3, that means our y values, or the range, is going to multiply by 3. So if I multiply both 4 and 9 by 3, we get 4 times 3 is 12, 9 times 3 is 27. Okay, that's if I vertically stretched that range. And then here I have a vertical shift up 2. So again, this is a vertical, so it only changes the y values. Shifting F2 means we're going to add 2 to both the y values. So 12 plus 2 is 14. 27 plus 2 is 29. So the resulting new range after both of those vertical changes is that our range is from 14 to 29 non-inclusive, and nothing changed here for the domain because there were no horizontal transformations of any type, so this one stays the same. That's all we've got today. I'll see you next class.